2 projects. In this video, we are going to explain about the project entitled as Classifying Scam Calls Through Content Analysis with Dynamic Sparsity, Top K Attenuation, Regularization. So before getting into the video, let me give you a brief description about the project. In today's digital world, scam calls have become increasingly sophisticated, making it difficult for people to identify fraudulent conversations. This project focuses on building an intelligent system that can automatically analyze call transcripts and accurately detect scam behavior. By using advanced deep learning techniques and a specialized top K attenuation mechanism, the model learns to focus only on the most important parts of the conversation while filtering out unnecessary information. This not only improves accuracy but also makes the system more efficient and interpretable. Through this project, we aim to demonstrate how modern AI can help protect users from deceptive callers and strengthen automated fraud detection. Coming to the abstract, this abstract explains that scam calls are becoming a serious threat, making it necessary to develop intelligent systems capable of automatically analyze call conversations to detect deceptive behavior. Traditional machine learning models struggles with noisy and unstructured call data and often fails to identify the subtle linguistic cues scammers use. To address these limitations, the project introduced a deep learning approach using dynamic sparsity, top K attenuation regularization, which allows the model to focus only on the most important parts of the call transcript while filtering out irrelevant information. This selective attenuation improves interpretability, reduces overfitting, and significantly enhances classification accuracy. Experimental results shows that this method effectively identifies scam patterns and provides a strong scalable solution for automated scam call detection. Coming to the existing scam call detection system generally use simple rule-based methods such as keyword matching or basic machine learning models like SVM, navy bias, and logistic regression. These approaches depends heavily on manual created features and fixed keywords list, which makes them ineffective against new or evolving scam strategies. They often fail to understand the deeper meaning, context, or tone of the conversation, which are important in identifying subtle scam cues. Even when neutral network models are used, their traditional attenuation mechanisms spread focus across too many words, creating noise and reducing clarity. Because of these limitations, current system struggles with accuracy, cannot generalize well of unfamiliar scam patterns, and are not capable of handling long, unstructured call transcripts effectively. Coming to the proposed system or base paper work, the proposed system improves scam call detection by using a specialized technique called dynamic sparsity top K attenuation regularization combined with a deep neural network. Instead of analyzing every part of the call transcript equally, the top K mechanism allows the model to focus only on the most important and informative parts of the conversation. This selective attenuation removes unnecessary noise, makes the model easier to interrupt, and reduce the risk of overfitting. The system works through a complete end-to-end pipeline that converts speech to text, generates contextual embedding, and then applies the refined attenuation technique to classify the call as scam or not scam. By focusing on key conversation segments and filtering out irrelevant details, the proposed system achieves higher precision, better adaptability to different scam patterns, and greater overall efficiency compared to traditional methods. Coming to the dataset used in this project is the scam or not scam call conversation dataset, which contains call transcripts specially designed for training and evaluating models that detect fraudulent phone calls. It includes a total of 800 conversations with 400 labeled as scam and 400 labeled as not scam, giving the model a balanced set of examples to learn from. These transcripts were collected from publicly available sources such as social media posts, new articles, and online discussion forums. And some additional synthetic conversations were created to cover more scam scenarios. Each entry contains a full dialogue from a call along with a label indicating whether the conversation is legitimate or fraudulent. Because the dataset includes many types of scam techniques and different conversational styles, it is highly useful for research in text classification, fraud detection, and advanced deep learning approaches like attenuation based model used in this project. Coming to the novelty or extension or enhancement or improvement. As an extension to the main system, we integrated birth embedding with a birth-based classification model, which significantly enhanced performance and achieved an outstanding 100% accuracy in detecting scam or spam texts. To ensure a fair and complete comparison, we also implemented all baseline models along with the proposed approach. In addition, we incorporated explainable AI techniques such as line and shape to highlight the most influential words and features used by the model during prediction, making a system more transparent and easier to interrupt. To make the solution user-friendly, we developed a Flask-based web interface that allows users to input text, receive instant scam detection results, and view top modeling insights directly on the results page, creating a practical and interactive system. Coming to the flow of the work, first we have import the packages. All the necessary Python libraries are imported to support data processing, visualization, embedding generation, model training, evaluation, XAI, and deployment. Next, we have data ingestion. The scam and non-scam call conversion dataset is loaded into the pandas data frame so it can be easily incepted, cleaned, and processed for further steps. Next, we have pre-processing. The raw text is cleaned by converting to lower cases, removing phone numbers, URLs, digits, punctuations, and stop words, followed by tokenization and stemming. Knowledge graph filtering is applied to reduce noise and standardize key terms. And next we have embedding or vectorization. The clean text is transformed into numerical representations using distilled birth embeddings, and TF-IDF vectors so models can understand and learn from the data. Next, we have data visualization. Exploratory visualizations such as label distribution, text length distributions, and word clouds are created to understand data patterns and check for imbalances. Next, we have label encoding. Scam and non-scam labels are converted into numerical form to make them compatible with machine learning algorithms. Next, we have feature extraction and data splitting. Features from embeddings or vectors are extracted and the dataset is split into training and testing sets to properly evaluate model performance. Next, multiple baseline models and advanced extinction models are trained and compared to identify the best performing approach. Next, we have evaluation. Models are evaluated using metrics such as accuracy, precision, recall, FN score, specificity, ROC, AUC, NPV, log loss, and confusion matrix. Explainable AI tools like Line and Sharp are used to explain model decisions. And next we have save artifacts. The best performing model along with pre-processing tools are saved for future use or development. And next we have Flask deployment. A user-friendly Flask web application is built where user can input text which is then pre-processed, embedded, and analyzed by the model and finally displayed with prediction results and topic model insights. The algorithms used in the project are, we used baseline models like D star, which is known as dynamic sparsity top K attenuation regularization, and SVM support vector mission, RF random forest, DT is known as decision tree, CNN is convolutional neural network, RNN recurrent neural network, NN it's a neural network, LSTM is known as long short term memory network, and as an extinction model we have used BERT, which is known as bidirectional encoder representations from transformers. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute this project, first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing users' requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. These are Jupyter Notebook files which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Get Started button. Now click on Get Started button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on Create an account so that all the given details are stored in signup.db and the login HTML will be opened, where we need to access the application by username and password. Then click on Sign In so that the prediction page has been displayed. In this page, we have Home button, Analyze button, Data Visualization button, Notebooks button, and Sign Out button. So firstly, click on Analyze button so that the scan call content analysis will be opened, where you need to upload the call transcript text input and analyze the content. So this is a upload call transcript. We need to upload a text input in this place. Let us check by giving the input. So we need to fill this with the text input and then click on Analyze the content. The given input will be pre-processed and the output will be displayed as non-scam and the confidence level will be 96.22%. The analyzed summary is given as legitimate call identified by using professional, respectful tone maintained, no urging pressure, standard conversation patterns. So here we have the original transcript which we have given as the input and the extracted information. The keywords are energy, kindly, name, service, electricity, account, bill, recent, share and company. And the quick actions are given as call appears safe, use caution, trust your instincts, proceed with normal precautions. And we also have the further information like analysis summary. And here we have analyze another call. So now let us give another input and check whether it is scam or not scam. Click on analyze content. So the input is pre-processed and the output is displayed as it's a scam. The confidence level is 58.57%. The analysis summary is a warning given, potential scam detected by urgent, pressuring language, suspicious payment request, request for sensitive info, threatening tone. The original transcript which we have given is this, and the extracted information like the keywords are payment, company, associated, greeting, date, money, outstanding, finalize, send, reaching. And we also have the quick actions to be taken like do not respond, hang up immediately, report the call, verify independently. And we also have some further information like common scam indicator detected. So we have seen the scam and non-scam information. And we also have an other button like print results so that whatever the results you have got by this input, you can have the print also. Then click on data visualization so that the graphical representation of the project graphs will be displayed. So first we have sample outcomes graph. The bar chart shows an equal number of scam and non-scam call transcripts with 400 samples in each class. This perfect balance ensures that the model does not exhibit bias towards either category and the evaluation metrics remain reliable. Balanced datasets are ideal for classification tasks because they prevent skewed learning and provide fair performance comparisons across models. In this case, the equal representation allows the models to learn scam and non-scam patterns equally well, contributing to the high performance observed in many algorithms, especially BERT. And next we have distribution of text lengths in words. The text length distribution graph shows how many words appear in each conversation transcript after pre-processing. Most conversations contain between 30 to 60 words, with a speak peak around this range, indicating typically calls length patterns in the dataset. A few transcripts are longer, stretching above 100 or even 200 words, but these are rare and represent extended call dialogues. Understanding text length is important for selecting model architectures. Models like RNNs or transformers can handle variable length sequence, while classic machine learning algorithms may require vectorization strategies. The plot confirms that the dataset contains relative short transcripts, make it manageable for most NLP models. And next we have overall word cloud of all clean text graph. The word cloud represents the most frequently occurred words in the entire cleaned dataset after pre-processing. Larger words indicates higher frequency and the visualization helps quickly identify common linguistic patterns or repeated terms across scam or not scam conversations. This overview provides insights into the general vocabulary distribution and highlights keywords that appear frequently in dialogues. Though individual scam or non-scam specific patterns aren't differentiated in this cloud, it helps to visualize, understand the dataset's dominant texture, structure, and token distribution after cleaning. Next, we have confusion matrix graph. The confusion matrix for the birth model demonstrates that the model predicted all classes correctly without making a single error. It classified all 80 non-scam calls as non-scam and all 80 scam calls as scam, resulting in 100% of accuracy. This outcomes highlights Bird's remarkable ability to understand linguistic cues, context, and sentence relationship within call transcripts. Such a perfect classification suggests that Bird can capture scam specific patterns effectively and is highly suitable for tasks involving detailed text interpretation. However, this also indicates that careful validation or external dataset is necessary to ensure that the model is not overfitting to this specific dataset. And next we have model performance comparison graph. The model performance comparison chart provides a comprehensive evaluation of all baseline and advanced models across multiple metrics such as accuracy, precision, recall, FN score, specificity, ROC AUC, NPV, and log loss. From the results, Bird consistently outperforms all other models, achieving perfect scores across almost every metrics. Deep learning models like CNN, RNN, LSTM, and NN perform strongly and remain close to each other, showing their capability in handling sequential text data. Classical models such as random forest decision tree and SVM are also shows competitive performance by falling slightly behind neural models. The log loss comparison clearly highlights Bird's superior confidence in its prediction, while decision tree shows the highest loss, indicating uncertainty and misclassification tendency. Overall, this multi-metrics comparison shows that transformers, especially Birth, delivers the most reliable and accurate results for scam call detection. Next, we have accuracy graph. This graph illustrates the overall accuracy of each model representing the portion of correctly classified samples among all predictions as expected from its top precision and recall. Birth again achieves the highest accuracy, meaning it makes no classification errors. NN and LSTM shows excellent accuracy, reflecting their balanced precision and recall. RNN and Random Forest also maintain strong performance. Decision tree and SVM shows moderate accuracy, while CNN completes the list with the lowest but still respectable score. This graph reinforces the trend that transformer-based and advanced neural network models outperform traditional methods in overall performance. Next, we have precision graph. This graph presents the precision scores of the same models. Precision evaluates how many of the predicted positives are actually correct, which is crucial with false positive carry high cost. Again, Birth leads with perfect precision, showing its predictions are entirely accurate among the positive outputs. NN and LSTM both scored 0.969%, indicating very high reliability in their positive predictions. Random forest and RNN also perform strongly. Meanwhile, decision tree and SVM exhibit solid but slightly lower precision. CNN has the lowest precision, although still relatively high. The distribution indicates that deep learning models generally outperform traditional models in terms of accurate positive prediction. And next we have recall graph. This graph compares the recall of different machine learning models. Recall measures how well a model correctly identifies all relevant positive cases, making it especially important in tasks where missing a positive instance is costly. In this graph, Birth achieves the highest recall, meaning it identifies all positive cases without missing any. Models like NN and LSTM also perform extremely well, showing that they rarely miss true positives. RNN and Random Forest follows with the recalls of 0.950%, indicating strong but slightly lower sensitivity. Decision tree and SVM shows moderate performance while CNN has the lowest recall among the group. Overall, both demonstrate perfect coverage of positive samples while traditional machine learning models shows comparatively low sensitivity. Next, we have F1 score graph. The F1 score comparison shows how well each model balances precision and recall, making it a reliable measure of imbalanced classification tasks. As with previous metrics, BERT again achieves a perfect 100%, indicating optimal precision recall balance. NN and LSTM both scores 0.969%, making them strong alternatives when transformer models are not available. RNN and Random Forest both achieve 0.950%, reflecting good overall classification capability. In contrast, CNN shows a lower F1 score at 0.906%, indicating challenges in balancing recall and precision. Decision tree performs better than CNN but still lags behind more complex models. SVM performs moderately but does not reach the capability of deep learning or ensemble based approaches. Overall, the deeper models consistently outperform shallower architectures across F1 scores as well. Next, we have specificity graph. The specificity graph measures each model's ability to correctly identify negative samples. Models with higher specificity makes fewer false positive errors. Again, BERT leads with perfect 100%, implying it made no false positive predictions. NN and LSTM both scores 0.969%, showing strong reliability in negative class detection. RNN and Random Forest also exhibit good performance, just slightly lower. SVM and Decision Tree shows modest performance, indicating more false positive relative to the others. CNN ranks the lowest here, suggesting it struggles the most with over-predicting positives. The trend shows that transformer-based models are deeper neural networks typically handle specificity better than shallow or tree-based models. Next, we have ROC and AUC graph. The ROC-AUC comparison graph evaluates how well each model separates the positive and negative classes across different classification thresholds. A higher ROC-AUC indicates a model is better at distinguish between two classes. In the chart, BERT scores the highest with a perfect 100%, demonstrating flawless discriminative ability on the dataset used. SVM and NN also perform extremely well, indicating robust generalization. CNN and RNN achieves identical values, showing strong but slightly lower performance. LSTM is also competitive, sitting just above RNN or CNN. Random Forest shows a slightly dip at 0.989% but still remains strong. The decision tree performs the weakest among the models at 0.919%, indicating greater difficulty in capturing complex patterns compared to the others. Overall, transformer-based and large neural models dominate, while simpler tree-based approaches struggle relatively. And next we have log loss performance graph. The bar chart compares the log loss performance of the several machine learning and deep learning models used in the classification tasks. Lower log loss values indicates better calibrated probability predictions. BERT achieves the lowest log loss, showing superior confidence and accuracy in its prediction. Neural models like NN, LSTM and RNN follows with relatively low losses, meaning they perform reliably. Models like CNN and Random Forest shows moderate log loss, indicating less consistency. The decision tree performs the worst with a very high log loss, meaning it probability estimates and unreliable and unstable. Overall, this plot shows the moderate transformer and neural architectures significantly outperform traditional ML models on this metrics. And next we have line explanation for text index graph. The bar chart visualizes the output of line method for a particular text sample classified as no scam. Each bar represents a word from the text and how much it negatively influenced the model's prediction of scam. Since all values are negative, it means these words push the model towards the not scam classification. Words such as greet, name, want, and chat had the strongest negative weights, meaning they are associated with harmless or normal conversational patterns. The further left and bar extends, the more it contributes to reduce the probability that the message was scam-like. In summary, this plot highlights which individual words reassured the model that the text was safe. And next we have Sharp water plot graph. This bar plot displays the mean absolute Sharp values for two features, feature 0 and feature 1, indicating their average contribution to the model's prediction. Sharp values measure how much each feature influences the model's output, with higher values representing stronger impact. In the graph, both features 0 and feature 1 shows nearly identical mean Sharp values, suggesting that the model considered them equally important when making predictions since the bars are horizontal and of the same length. This indicates that no single feature dominates the model's decision-making process. Instead, both contribute similarity to the overall predictive behavior. And then click on Sign Out. So finally, this project demonstrates that applying dynamic sparsity with top K attenuation regularization significantly improves the accuracy and robustness of scam call classification through content analysis. By encouraging the model to focus only on the most informative parts of the call transcripts, the approach reduces noise, enhances interpretability, and leads to more efficient computation. The results show that the proposed model not only outperforms baseline models but also offers a reliable framework for real-world scam detection system, ultimately contributing to safer communication environments. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.